Computing matrix inverses is tedious. Gaussian elimination, cofactors, adjugates, all expensive, right? But there's a family of matrices where the inverse costs nothing. Here's a 3 by 3 matrix P. Its first row is 0, 0, 1. Its second row is 1, 0, 0. And its third row is 0, 1, 0. Now flip it across the diagonal to get P transpose. P transpose has first row 0, 1, 0, second row 0, 0, 1, and third row 1, 0, 0. Now multiply P times P transpose. The result is the 3 by 3 identity matrix. That means P inverse equals P transpose, completely free. These are called permutation matrices, and here's why this always works. A permutation matrix starts as the identity. Here is the 3 by 3 identity matrix. Ones on the diagonal, zeros everywhere else. Now let's rearrange its rows. We swap rows 1 and 2. Row 1, which was 1, 0, 0, slides down, and row 2, which was 0, 1, 0, slides up. After the swap, row 1 becomes 0, 1, 0. Row 2 becomes 1, 0, 0. Row 3 stays 0, 0, 1. This result is P12. Now here's the key idea. Left multiplying any matrix A by P12 performs that same row swap on A. Why? Look at the 0, 1, 0 pattern in row 1 of P12. When you multiply, that pattern selects row 2 of the target matrix. The 1, 0, 0 pattern in row 2 of P12 selects row 1 of the target. So left multiplication exchanges rows. For completeness, right multiplication by P12 would exchange columns instead, but we focus on rows here. Let's verify this with a full matrix multiplication. P12 is the matrix with rows 0, 1, 0, then 1, 0, 0, then 0, 0, 1. We multiply this by matrix A, which has rows A, B, C, then D, E, F, then G, H, I. To find entry 1, 1 of the product, we take the dot product of row 1 of P with column 1 of A, and that gives us 0 times A plus 1 times D plus 0 times G, which equals D. Continuing across all of row 1, the same pattern gives us D, E, F. Notice this is exactly row 2 of the original matrix A, now sitting in position 1. For row 2 of the product, the dot product of row 2 of P with the columns of A yields A, B, C. The original row 1 of A now in position 2. Row 3 of the product gives G, H, I completely unchanged. So the final result is the matrix with rows D, E, F, then A, B, C, then G, H, I. Rows 1 and 2 of A have been swapped exactly as we predicted. Now let's count all the permutation matrices for the 3 by 3 case. 3 rows can be arranged in 3 factorial ways. That's 3 times 2 times 1, which equals 6. Here are all 6 permutation matrices. First, the identity matrix I, where no rows move at all. Next, 3 single swaps, P12, which exchanges rows 1 and 2, P13, which exchanges rows 1 and 3, and the P23, which exchanges rows 2 and 3. Each of these swaps exactly 2 rows while leaving the third in place. Finally, there are 2 cyclic permutations. The first sends row 1 to position 2, row 2 to position 3, and row 3 to position 1. The second reverses that cycle, sending row 1 to position 3, row 3 to position 2, and row 2 to position 1. That accounts for all 6. For a 4 by 4 matrix, 4 factorial gives 24 permutation matrices. For 5 by 5, 5 factorial gives 120. The growth is rapid. These matrices form a closed family. Multiply any 2 permutation matrices, and the result is always another permutation matrix. Let's see an example. Take P12 times P23. P12 is the matrix 0, 1, 0 in the first row, 1, 0, 0 in the second row, 0, 0, 1 in the third row. P23 is 1, 0, 0 in the first row, 0, 0, 1 in the second row, 0, 1, 0 in the third row. Now let's compute their product step by step. For row 1 of the result, we take the first row of P12, which is 0, 1, 0, and dot it with each column of P23, we get 0, 0, 1. For row 2, the row is 1, 0, 0, giving us 1, 0, 0. For row 3, the row is 0, 0, 1, giving us 0, 1, 0. So the product matrix is 0, 0, 1, 1, 0, 0, 0, 1, 0. That's exactly the cyclic permutation matrix C1 from our earlier list of 6. A swap followed by a different swap produces yet another permutation. The product never leaves the family. We've seen the full family of permutation matrices. Now let's explore their inverses. Take P12 and multiply by itself. P12 is the matrix with rows 0, 1, 0, then 1, 0, 0, then 0, 0, 1. We write P12 times P12. Row 1 of the left P is 0, 1, 0. Dot this with column 1 of the right P, which is 0, 1, 0. We get 0 times 0 plus 1 times 1 plus 0 times 0, which equals 1. Now dot row 1 with column 2, which is 1, 0, 0. We get 0 times 1 plus 1 times 0 plus 0 times 0, which equals 0. And dotting row 1 with column 3 gives 0. So the first row of the product is 1, 0, 0. Applying the same process, row 2 of the left matrix is 1, 0, 0. Dotting with each column gives us 0, 1, 0 for the second row, and row 3 is 0, 0, 1, which gives 0, 0, 1 for the third row. The full result is the 3 by 3 identity matrix. P12 squared equals the identity. If you swap rows 1 and 2 and then swap them again, you're back to where you started. Right? This means P12 is its own inverse. But not every permutation matrix is its own inverse. Consider the cyclic permutation matrix P, which equals 0, 0, 1 in the first row, 1, 0, 0 in the second row, and the 0, 1, 0 in the third row. This cyclic permutation sends row 1 to position 2, row 2 to position 3, and row 3 back to position 1. Now let's compute P times P to see if P squared equals the identity. Working through the multiplication, for entry 1, 1, we get 0. For entry 1, 2, we get 1. For entry 1, 3, we get 0. Continuing for all entries, the result is 0, 1, 0 in the first row, 0, 0, 1 in the second row, and 1, 0, 0 in the third row. This is the reverse cycle, not the identity matrix. So P squared does not equal the identity. We can cross out the idea that P squared equals I. This means we need a general rule for finding inverses of permutation matrices. And here is the answer. For every permutation matrix, P inverse equals P transpose. This is a universal rule that works for all permutation matrices, not just the special ones that happen to be their own inverses. Let's verify this. P is the matrix 0, 0, 1 in the first row, 1, 0, 0 in the second row, 0, 1, 0 in the third row. The transpose operation flips rows into columns. So P transpose is 0, 1, 0 in the first row, 0, 0, 1 in the second row, 1, 0, 0 in the third row. Now let's compute P times P transpose to see if we get the identity. For entry 1, 1, we take row 1 of P, which is 0, 0, 1, and dot it with column 1 of P transpose, which is 0, 0, 1. That gives 0 times 0, plus 0 times 0, plus 1 times 1, which equals 1. For entry 1, 2, we dot row 1 of P with column 2 of P transpose, 0 times 1, plus 0 times 0, plus 1 times 0, which equals 0. Entry 1, 3 similarly equals 0, so the first row of the product is 1, 0, 0. Working through row 2 of the product gives 0, 1, 0, and row 3 gives 0, 0, 1. Therefore, P times P transpose equals the 3 by 3 identity matrix. This confirms that P transpose is indeed P inverse, just as the general rule promised for every permutation matrix. Why does this work for every permutation matrix? Let's think about the structure. Each row of a permutation matrix has exactly 1, 1, and the rest are zeros. Each column has exactly 1, 1 as well, with the rest zeros. Now consider the product P times P transpose. The entry in row I, column J of this product equals the dot product of row I of P with row J of P. Case 1. When we dot a row with itself, the single 1 aligns with itself and every 0 aligns with a 0. So the result is 1 squared plus 0 squared plus 0 squared and so on, which equals 1. Case 2. When we dot two different rows, their 1s sit in different column positions because no two rows can have their 1 in the same column. So the 1s never overlap and every product in the sum is 0. The dot product is 0. This means the diagonal entries of P times P transpose are all 1 and the off-diagonal entries are all 0. That gives us the identity matrix every single time. This is why permutation matrices are a special case of orthogonal matrices. The broader family of matrices where Q inverse equals Q transpose. The n by n permutation matrices satisfy all four group axioms. Let's check them one at a time. First, closure. The product of two permutation matrices is itself a permutation matrix. If you rearrange rows and then rearrange rows again, the result is just another rearrangement. Second, identity. The identity matrix I belongs to the family. It's the permutation that leaves all rows in place. Third, inverses. P inverse equals P transpose. And since the transpose of a permutation matrix is also a permutation matrix, every element has an inverse within the group. We proved this property in the previous frame. Fourth, associativity. This is inherited automatically from matrix multiplication, which is always associative. Since all four axioms are satisfied, the n by n permutation matrices form a group. And this group is known as the symmetric group as sub n. Now here is a major application. In LU factorization, when a pivot turns out to be 0, we multiply by a permutation matrix P to swap rows and fix the problem. This gives us the factorization PA equals LU, with P highlighted as the key addition. The beauty is that undoing the permutation requires no elimination at all, it's just a transpose. Since P inverse equals P transpose, reversing the row exchange is computationally cheap, and that's the final tagline. To undo a row exchange, just transpose.